Okay, nice. So, I'm Anton from Fresha. We are doing a lot of exciting data engineering stuff, and I'm about to tell you something that we recently actually played with, and we have something to tell. So, let's start simple from who actually is using Flink on production. Okay, that's gonna be interesting. Okay, who have heard about Flink? Okay, it's even more interesting. So let's start then super simple. So what is Flink in high level? So it's basically some streaming engine, distributed apparently, with local state that is used for computation. Why is it important? Because your local state is actually pretty decent for your performance. So you can actually oh, I need to process the data and emit some records as quick as I can. Okay, all the state in my local state, so I can quickly query and issue. So it's fine until that becomes a problem, when the state is too huge. So what to do? Imagine that you have like hundreds or thousands of pipelines where you need the same data. So imagine that the whole your business is actually around some bookings or orders table. So every pipeline that you wish to do the enrichment or some dimensional enrichment would require this table. And if you don't have like some proper measurements to have this state bounded in some case, then you would end up backfilling this state constantly. It's a problem, and it's a complicated problem because sometimes you cannot even have that big local state, and that means that you need to do some clever workarounds, as I call it, because one clever workaround is basically to have some TTL and say like, okay, my state is bounded and I only care about, let's suppose, like 3 months. If you are lucky with this stuff, then it's fine. If it's not the case and you need the whole state, that's a big of a problem. So what you can do, you can basically have some workarounds when you have some side pipeline, when you say like, okay, most of my state is actually bounded for example, like 1 year. And then when something is not quite like in this range, I can actually batch async execute it and then get the result to the pipeline. It works? Yes. Is it real time? Well, not really. Is it a problem? Depends on your business and your work on your case. Yeah. So basically, then the question: how do we use Flink? Basically, that's an architecture of our data lakehouse at Fresha, and it's super simple. So it's simplified for you, just to get you the idea how Flink and other stuff can be used there. So basically, we have a sources plane. It's super simplistic. So we have a Postgres database. Then we have Kafka Connect with Division, delivering like CDC records to Kafka. And then we basically have a compute plane. It's Flink and Spark to do the enrichments. And basically, then we produce this output either to our lake plane. So we have like Pymon and Iceberg, or to our things plane that is can be the same Postgres, Kafka, some intermediary topic, Iceberg, or Starox. So how many of you have heard about Starox, for example? Okay, so let's imagine that it's Trina. That's better? Okay, but basically, yeah, you just use some clever federation to query your lake plane, and yeah, it just works. So this is the architecture that we run at Fresha, and the problem is, imagine, oh, maybe it's a better example. Like, imagine that here is ClickHouse, or some analytical engine when you need to do some white tables, to run some white tables. So in order to do these white tables, you need to join these tables and deliver like a flattened records to this table. That's a problem because you need to do the join. And this join needs to be done with some compute plane, for example, Flink. And as I said, if you have some bookings or orders table that is doesn't have sensible bounds, you end up with a large state. The solution to this problem? Yes, we have. Anton Fluss. So it's basically, how to define it? Basically, let's call it a storage engine, because some people actually feel that right now Fluss is some an extension to Flink to have fast joins or kind of like have some state that is shared between Flink processes. But some people actually kind of like define it as a generic open table format as well, because it's actually like a table format. So it's actually files on some kind of like storage. So let's talk about what is actually kind of like depicted in this diagram. So you have your database logs. So this is kind of like streamed in real time through Kafka to Fluss cluster. So Fluss cluster consists of some leader and followers tablets. So basically servers that actually have some local state and remote state. And then there is an optional tiering to lakehouse storage. So you can actually have this state that you want to externalize in lakehouse, in Iceberg or Pymon or Lance or any other kind of like format that Fluss would eventually support. And then what you can do with this, you can basically have union reads, lookup joins, and lakehouse analytics, because I mean, like you use Fluss in order to get the data inside your cluster, and then there is a tiering job that actually delivers this data into Iceberg, and then you can query it with Spark, Trina, or any other kind of like generic query engine that supports this table format. Okay, that's nice. So let's actually zoom on some parts of this process. So this is union read. So what is union read? It's basically, imagine that you have Fluss cluster. So you can treat Fluss cluster as a real-time layer that your data is specifically kind of like optimized to be queried in real time. Treat it as an index, for example. Yeah, it's exactly kind of like RocksDB snapshot and indices and whatever. And then you have a tiering, and this tiering is actually getting to lakehouse storage. It's a bit of simplification because there are different types of tiering in Fluss. But let's focus right now that basically there is a real-time layer, and this is historical layer that you can query with lakehouse analytics engines and whatever. What happens if you want to read some data from your Fluss cluster? Basically, what you expect is real-time layer. You access real-time layer, you get the data, and then you want some kind of like a consistent view where this data is unioned with some tiered data that is actually kind of like in your lakehouse storage. And that's the best part, that basically when you do it, it automatically understands where this separation boundary is lying between Fluss real-time data and lakehouse data. So that's neat. So let's discuss a little bit the cluster architecture. Basically it consists of like some zookeeper node for coordination. Then there is a leader coordinated server that can be used as well for kind of like storing data, but it's responsible for doing this tiering, doing these snapshots and other kind of like stuff when you need coordination from zookeeper eventually. So then there are tablet servers. They all coordinate and exchange information between each other. And then there is a client that can do real-time reads, historical reads, and it's also a little kind of like narrow green lane that is called object storage. And this is a little complexity that wasn't introduced in the previous diagram, because I should say that it's actually kind of like there are two types of tiering supported by Fluss. So one type of tiering is internal tiering. So it means, imagine that I have real-time data. It's optimized in a row-based fashion. So I can literally quickly stream and get this data. It's because it's in my kind of like a local state of this Fluss cluster. What actually happens in order to increase durability and in order to actually kind of like reduce the state, you have an internal tiering in arrow-based format to object storage, and this is about this. And then you have lakehouse storage, and it's external tiering. So there is two types of tiering. That's why I call Fluss as a storage engine, because it's actually kind of like behaving as a storage engine and have a different retention boundaries for the data that is flowing and you want to query. And the best part is basically Fluss unifies this data and provides you a consistent view. So you don't need to manage some offsets or kind of like reason about like where the boundaries of your data is actually lying. Storage architecture. So we discussed like class architecture. Now it's time for storage architecture. Storage architecture is actually pretty simple because let's suppose that you have like a table. A table consists from some logical layers. So this is kind of like partition column. It's only logical, so it's not like files something. Then you have a bucket layer, and this bucket layer is actually corresponds to two types of tablets. There is a log tablet that is basically you can treat as a wall. And this wall accumulates the changes, and eventually these changes are rolled out as segments to this internal tiering. And these log tablets are actually replicated between Fluss cluster nodes. And then you have key value tablets, and key value tablet is basically a single one, but it's backed by and durable by a log tablet. So basically, when you want to have like a primary key table where you can aggregate by primary key, you use key value tablet that is using the abstraction provided by a log tablet that is actually kind of like wall with tiered and rolled out segments to object storage. And yeah, each key value shard actually corresponds to some RocksDB instance. I have a question. Have you heard about Pymon? Okay, so this actually architecture about like logical separation by partitions and then by buckets being backed by some kind of like tablet in this case, but in case of Pymon is actually the actual bucket in your object storage is actually pretty similar. And the initial implementation of external tiering to object storage was Pymon. So that's exactly kind of like not a coincidence. And I guess with some settings, you can actually adjust bucketing and partitioning in a similar fashion between Fluss internal storage format and Pymon, for example. With Iceberg, it's a little bit more complicated, but for Pymon, it's easy and kind of like logical thing to do. Okay, let's move on. So, tiering. As I said, there are multiple facets of tiering. So there is log tablets that are basically are rolled out on some kind of like a basis on object storage as a tiered segments that can be downloaded by need, and then they're used as a wall for key value tablets that are basically a kind of like a base of your tablet tables. And as I said, like log tablets are replicated, and key value tablets are not replicated. So key value tablets are basically have a durability guarantee by RocksDB, and then there is not exactly like a tiering, but basically RocksDB has snapshots, so you can have a snapshot, and then when you need to recover, because imagine this stuff is not replicated. So what happens if we actually need to move this stuff to another node? It would be a problem. Well, kind of, because you basically can restore from a snapshot from RocksDB and then apply tiered segments. So that's the whole idea. Okay, let's move to some interesting part. So DeltaJoin, that's a new thing in Flink 2. Oh, man, I'm doing something wrong. I don't know.
Maybe it's not well inserted.
Okay, let me try to fix it. I pray you. Okay, I'll try to not to move my laptop, but let's continue. So DeltaJoin. What the heck is DeltaJoin? So basically, it's an innovation introduced in Flink 2, and it's actually possible because Flink 2, like the most recent major version, introduced a lot of changes to execution model to allow asynchronous execution and asynchronous key ordered execution. So it means that you can process the updates to different keys separately in parallel, but the updates for the same keys would be ordered and executed in sequence. It's big because you can actually have more I/O and CPU parallelization just for free, just by using this model. So the idea. Imagine like in a normal stream-to-stream join. So you need to react when something appears on the left side and when something appears on the right side. So new message comes from left side. So I need to support left state. So left state, so for example, imagine that it's kind of like a join between customer and orders. And I have some customer kind of like changes and some order changes, and I wish to react and emit like a flattened record, a join. Basically, when something happens with any of these kind of like counterparts. So it means that I need to store it in the local state, and that's exactly like these pictograms are actually depicting. So you have left state and right state, and actually kind of like the process is super simple. So I receive a new record, I find all the counterparts in my right state, and if I receive from something from the right side, I need to do lookup on the left side. So it means that I need to support like this big state on presumably on the left side and on the right side. What is the innovation that was introduced by Fluss? Basically, if you use DeltaJoin, it's not exactly by Fluss. No, I think like it's a generic framework by Flink, but right now it's usable mostly by Fluss. So it means imagine that you have Fluss. So it means you don't need this state because this state is externalized in Flink, in Fluss. Sorry. So it means that instead of like having a large state that you need to support and actually kind of like place next to the executors, you right now only need to actually have some caches, some LRU caches for some frequently accessed keys. And if something goes wrong, you can asynchronously query Fluss. So these kind of like LRU caches are actually guaranteed by Flink, and asynchronous model that I talked about before is actually guaranteeing that you basically issue a lot of lookups. And because Fluss is very real time, remember I said that basically the Fluss internal format is basically your local state as well. And then it's tiered, and that's why you not overbloat your state. So it means that these kind of like updates to a separate keys can be executed in parallel, and they would be kind of like in sequence, and everything would be all right. So this is kind of like an innovation, and it changes a lot of patterns that are available for Flink. So this slide is about Pymon and comparing to Fluss, because Pymon was advertised as a file format that was exactly invented to support more streaming workloads. So what does it mean? Imagine that I want to join some table where the primary key is customer ID and another table where there is the same primary key. It's possible. You just kind of like have an index and you look up, because basically under the hood, Pymon is LSM3. So it means that it's incrementally compacted. So you stream the data into Pymon table, some files ends up in object storage, then the changes are accumulated, and then you need to apply them and actually kind of like clean up all the mess that was created by writing to this bucket. And it means that by primary key, you can easily search. It's neat for compaction and kind of like streaming, but it's not that great when you want to actually kind of like join by another key. So for example, let's suppose that you have like a table with primary key customer ID and another table where there is a customer ID, order ID. You're out of luck because you need to construct some aggregated state, and this aggregated state would be some customer ID and a map of matching order ID, and you need to support an additional Flink job or somehow construct the state to actually make it queryable. So no luck. Fluss, on the other side, is actually supporting with this kind of like RocksDB implementation and tiering. It actually supports this workload. So if you have some bucket with customer ID, and then you have a bucket with sub-branch of customer ID, and then a sub-branch of order IDs, you can basically specify, okay, I want to join all customer IDs, and then provide me where they have matching orders. It would match because it's kind of like literally sorted in the similar way. So it works. So in Pymon it doesn't work. You need to do an additional work. In Fluss it works natively. So how is it possible? So I guess now it's time to talk about like this asynchronous model execution that was introduced by Flink, Flip 425 and Flip 419. So basically the idea is this kind of like, let's focus on Flip 519 because the previous Flip that I mentioned is quite complicated, and it's basically a basis for new disaggregated storage backend that was introduced specifically for Flink 2. And it means that there is a lot of things to discuss. So let's focus on this kind of like diagram. What is shown in this diagram is basically, imagine that you have like some updates for a specific key, and this is the diagram actually depicts like one key, and these events A1, A2, A3 is a different updates that are taken some time to actually to be processed. And it means with this kind of like idea of keyed async wait operator, you process different keys for your lookup joins in a separate kind of like threads, and it's basically an independent line of execution. And then you have a guarantee that basically when you receive the data, all the updates for the keys for the same keys will be ordered and would be kind of like sequentially processed. So that's why you can basically, if you have your data in Fluss internal format, it will be returned quicker. If something is not in Fluss internal format, you need to download this tiered segment and you still get the data, but it would arrive ordered. So if you have, there is kind of like a limitation arising from this, because imagine if you have a high churn table, it would be problematic, but we will get to this on later slides. So let's talk actually about limitations. So currently some of the limitations are basically because it's very new. So Fluss was kind of like now is a part of Apache Incubator project. It's used in Alibaba and Taobao actually uses it extensively, but it's kind of like their own adaptation of Fluss. So open source Fluss doesn't have all the things that Alibaba Fluss has that they use internally. So they eventually release it and kind of like get rid of some Alibaba internal components, but it means that it's still early days for Fluss and it's early days for Flink DeltaJoin. But that would actually change, and it actually marks a very important landmark for Flink and real-time streaming, because before it was all about like, I need to process my records as soon and as real time as I can. And the answer for this was always kind of like, I need to trade a bloated state for the real timeness and latency. And if something happens, yes, I need to backfill, I need to invent some kind of like trade-offs and workarounds, and it worked. Right now, it's shifting more to the idea of externalizing state and making execution more stateless, and to use some caching, tiering, and other kind of like, like infrastructure-related optimization just to make the life of you as a data engineer dealing with streaming a lot easier. So topology, it's the first limitation. Only stateless operators are allowed between source and join. So it means that you don't, you're not allowed to use some clever aggregation, min, max, and other stuff, because it's actually kind of like a separate state. So right now they are not supported. It's not very kind of like complicated to add it, but it's just kind of like early days, as I said, like, so just to be aware. Then multi-join. That's another interesting kind of like thing. So as you know, like Flink currently doesn't support multi-join, but it would be supported like pretty soon. And the same kind of like applies to Fluss. So if you want to realize that I have like an externalized state in Fluss in some kind of like Fluss table, and I want to just query this table, right now is impossible, because you can only kind of like externalize state for a single join. You cannot say like, okay, I want to join my order with some kind of like, I don't know, like sale items and sale item with sale and whatever, because it needs to have a separate state. So that's a limitation. Changelog support, streams with update before rejected, because when you write to Fluss, actually kind of like you get like the aggregated state in your key value table, so you don't know what was deleted and whatever. So update before, right now I just rejected, and if you have like in your changelogs update before semantics, then there is like a warning that calls like, okay, you know what? Flink DeltaJoin cannot be used here, so it's only kind of like the same stateful stream-to-stream join is used. Then delete semantics is kind of like another technicality, so only one delete on one side is supported, still related to this limitation. And consistency, we will get to this later, because it's hard to explain just in words, so I prepared a diagram. Then cache. So you need cache, and you need to kind of like adjust your cache depending on your workload, how kind of like big these caches should be. And miss triggers async probe. So if you kind of like don't have the data in your caches, then you need to go to Fluss and presumably to the tiered segments, and it will be a little bit slower. That may be a problem or not, depending on your workload. And plenary write. As I said, like if something is not supported right now, planner just silently with a warning tells you kind of like, okay, it's not supported. It would be kind of like just a regular join. So about eventuality. So I'm comparing here kind of like Flink and Fluss and Fildera. So Fildera is another compute engine. It's very neat and mathematically kind of like sound, and it actually relies on totally consistent data, because the whole idea of Fildera, I don't think that you know what is Fildera. Do I assume correctly? Okay, yeah. So the idea of Fildera, imagine that you have like some computation, and when some new records arrive and you have like, let's imagine 50 joins, and you need to understand what are the records in all of these joins would be emitted related to these small delta records that you received. It may be 10 records, it may be 15 records, or it may be the whole state, kind of like thousands or millions of records. So how does Fildera achieve it? It's actually pre-materialized all the intermediate state with some kind of like index-like data structures. So it means that you can actually can query and say like, okay, during the last epoch, it was kind of like the change of this. So I need to emit like 3 records because these 3 records are actually related to what changed. So it means it's absolutely consistent, but at the same time, it actually means that you need to store a lot of state. And it can be a problem, but basically it's the most correct engine if you need to do stream transformation. So take a look if you are interested. So basically with Fildera, as you see, I have like an order emitted, and then I have like initial record order 1 and customer version 1. So order emitted, then timestamp 2 is kind of like passed. Order 2 is emitted. What it means that basically in Flink state, Fluss state, you actually have like 2 versions of this data. Is it a problem? Depending on your sync, because if your sync from Fluss is actually kind of like supporting idempotent and kind of like deduplication, then it's not a problem, because you would only get like the last record, and you have some kind of like a formality about like how to deduplicate this stuff. But for Fildera, it would just wait until the checkpoint where the epoch has finished. And once the epoch has finished, you actually get a consistent state. So this is like a converge state. Take a look. It's exactly kind of like how Fildera would actually do this. For Fluss, because the joins are asynchronous and kind of like a best effort, it's actually kind of like eventually consistent. So if your sync supports this kind of like behavior, when you can deduplicate, it's all right. If your sync doesn't support, then you have a problem. It's a trade-off, as always. So where kind of like Fluss asynchronous DeltaJoin model works and when it breaks. It's very simple. As I said, like imagine that you have like high churn join. So it means like you have sales and inventory, and with a change of sales, you have like a change of inventory, or some with a change of inventory, you have like high cardinality updates to the sales. So imagine that you kind of like update inventory, and you need to change every sale that reference this inventory. So it can, let's say it would be kind of like 2,000 records that you need to emit and update. Then it would be a problem, because depending on the size of your LRU cache, then it would mean that you need to actually go and fetch first from Fluss, and then you need to go from tiered segments, and maybe worst case scenario, you need to go to actual lakehouse, fetch the data from object storage, and it would be super slow, and it would mean that your caches would be constantly churned, and it will be lookup storm, and actually it wouldn't work. So as always, if you can, it's mostly suited for dimensional enrichment joins. If you need something that is kind of like emit records as something has changed, maybe Fildera would be a better way, because they actually kind of like have a DBSP, the full differential change engine that actually processes the records and understands what has changed, and they emit it instantaneously. But it's a trade-off, because Flink of Fluss is just cheaper to run. So As I said, like I compared fill data, Flink Fluss, then rising wave, and yeah, I think like I already told about fill data. So it's kind of like the whole idea is pre-materialized state and incremental indices, and then at every moment of time you can actually reason about like what should be emitted to the next stage. With rising wave, it's actually kind of like pretty similar to Flink Fluss, but the idea is well, it's an oversimplification because they have a lot of different kind of like changes, but to give you the simple idea, imagine that you have stateless compute actors, but the shared storage is actually guaranteed by multi-tiered cache. So it's just kind of like, okay, I do the same as Flink and Fluss, but in the end, it's all cached. So if my frequently accessed data, I can fetch it and rely on the performance of my storage implementation. They actually run their own implementation of cache, and it's called Hammock Cache. Very interesting kind of like design. So I recommend to take a look as well. Okay, so conclusion. So it's only like 4 bullet points. So that DeltaJoin is actually kind of like an attempt to externalize state and only rely on some bounded caches to actually run really quick real-time transformations and enrichments and whatever. Prefix lookups are actually pretty useful to support different kind of like join patterns, and Fluss implement this. Then there is enrichment joins, but it's the most suited. But if you want to avoid problems with performance with Fluss, just watch out for the scenarios when you have like when a single update can cause a high churn update on another side of the join. It would be disastrous. And then various engines provide their own answers for bloated state with the different trade-offs, because Flink Fluss is just like a native Flink answer to kind of like externalized state. Then if you want to use rising wave, it's kind of like an idea of kind of like caching as much as you can, all the intermediate caches. And then there is a fill data where the idea is basically, okay, if I have an incremental engine and every point of time I can reason what actually is changed on the downstream pipelines, then maybe I can just kind of like pre-aggregate, pre-materialize these indices, and then every time I can reason, and that's all. It's very expensive in some sense, but once it works, it's actually very computationally sound, and it's just a question how you need to support these kind of like large state. So currently they have different backends for this implementation. So, okay, so that's the end. So my name is Anton Borisov. So if you want to chat with me, so there is a LinkedIn link here, and I also write some articles about data lakes, data engineering stuff, Postgres, and other kind of like stuff. So if you're interested to read something, welcome. Yep.
Do you need Flink to run Fluss?
Yes. Right now you need to run Flink to run Fluss, because it was actually kind of like created as some kind of like extension to Flink. But the idea is basically to use it eventually as some generic file format, because right now the integration between Fluss and Trina is developed. Then the integration with Fluss and Starox is actually being actively developed, and basically nothing prevents to actually use it as a storage engine. Because as I said, like I deliberately avoided to call Fluss as some kind of like a file format. It's like a storage engine, like a generic one, and it shouldn't be related to Flink. Right now it's related because it was just invented to solve specific problems that were introduced by the model that Flink runs, and that's all.
What does your company do?
Okay, Fresher is actually kind of like a booking solution for fashion industries. So we have a lot of bookings, and as I said, like it's a problem because for some reason our data model doesn't allow us to actually trim these bookings. So users can change booking back in time. So it means that we need to support these kind of like large state computations. That's why when we use Flink, we're actually interested in ways to reduce the state. That's why all the fuss around Fluss, you know.
Is it because you're using Postgres or something to like as the transactional database?
Yes, we use Postgres as a transactional database. So yes, maybe it's related because, like all the data is highly normalized in Postgres. And then when you need to use it for analytics or some enrichments, then you end up with 15 joins just to model some simplistic thing. And usually it's kind of like you either kind of like flatten it heavily. So for example, to run some kind of like report in ClickHouse, then I need to actually kind of like flatten this data. And there is a trade-off. If I want this kind of like data to be as close to real time as I want to use a real-time engine. If I don't care, so I can run some batch job and process it with Spark and whatever, like overnight, and that works as well. But we are mostly interested in real-time data to power out our dashboards, some real-time analytics, customer analytics. That's why Flink.
What is the kind of volume? Like, no, it's like a second, so you don't.
Okay, the volume is actually kind of like, I think like we store around 1 terabyte in our lakehouse. So most of this stuff is actually kind of like being run through Flink, but because we are running Starox, we don't exactly need to use Flink all the time because Starox supports like joins natively, so you don't need to prepare a flattened data model. But when you want to actually kind of like for performance reasons and other stuff, you wish to use Flink. So for example, imagine that you have like a transaction and then transaction details, because transactions like Postgres modeling, like basic one. So transactions are used for some kind of like changes that are kind of like high churn. And then transaction details are actually kind of like once created, they never change. You want to separate this load because it's actually kind of like more beneficial for performance. But during querying, it actually makes more sense to actually join this data between together because they actually relate one-to-one to each other. So it makes a lot of sense to process this join in Flink and then emit just an updated record. And in this case, Flink is actually kind of like doesn't need to hold a lot of state because once transaction detail was created, then there is a matching transaction here. So you can just join and support like, I don't know, TTL of 1 hour just in case. And that just works. But in case of, for example, bookings table, because bookings table is actually the main table for Fresher, it means that you need to use it in a different workloads. And depending on the workloads, sometimes you cannot kind of like trim your state as much as you can. Yep.
So how big is the biggest state then that you have?
Biggest state?
Yes.
Oh, I think like biggest state, care pipeline, I assume. I think like it would be around like 300 gigabytes because, as I said, like booking table alone is something like more than 100 gigabytes for sure. Most probably it's already like 200 gigabytes. And imagine that you need to actually every join to bookings table, you need a state, like a local state, because as I said, like the devil is in the details. Because if I want to support like a state for joining like bookings and booking time segments, it's one state. When I join like booking and some sale, it's another state. So I need to duplicate it. So I mean, like we are running all kind of like optimizations and clever workarounds to do this, but it's still kind of like limited. So, yep.
How do you use Flink? Like, do you use a managed version by a specific provider or do you self-host it?
Yes, we self-host it. So there is a Flink operator, and we basically deployed it on our EKS, and it just works. It's kind of like an interesting learning experience by itself because Flink is somehow a little bit notorious to be not so user-friendly from the beginning, but right now it's actually working and it's pretty fine. And actually, recently I was at Flink Forward Barcelona, and it's actually improving a lot because this Flink operator now supports like blue-green deployments. So it means imagine that you are running like some Flink pipeline and you process like a lot of data and accumulate like, I don't know, like terabyte of state. In case of LinkedIn, because they run Flink and they had a talk about like handling large state, it's a problem. So how to migrate these old pipelines without downtime to another kind of like version of Flink, because you want to use disaggregated state, you want to use DeltaJoin. I mean, like that's the whole idea. So in this case, you need to orchestrate it kind of like cleverly, and that's kind of like managed solution offers this kind of like in some fashion. But if you run it by yourself, you need to solve it by yourself. And before it was like a really big problem. Right now there is kind of like some PRs are created. Actually, I think like Apple Maps created these PRs because they needed to actually do this like exercise. And then there was a talk by Shopify where they used it and they actually said like, thank you. So community is very active in Flink, but experience can be different.
Okay.
It can be executed in on-prem as well, right? On-prem Kubernetes cluster as well.
Yes, I think like there are multiple offers of Flink, like starting from AWS, Ivan, and kind of like other, even Verberica, the creators of Flink, they have their own Verberica platform when they actually have even kind of like an implementation of streaming lakehouse. So, yeah. Yep.
Have you tried Flink 2 yet?
Yes, we tried and it's actually working. Yeah, I mean, like, it's kind of like the main advantage of Flink 2 was disaggregated state. So as I said, like, okay, you have a state, this state is very large. So how do you handle this state? So before it was kind of like, okay, I need to actually kind of like have it in memory or kind of like externalize it somehow with TTLs and other stuff, so other workarounds. But usually it was kind of like, I have a kind of like big pipeline, I need a lot of big machines with a lot of memory, so that's how it works. Right now, or kind of like offload, because there is a state and there is a RocksDB state used for checkpointing. So it's also a problem because the bigger the state, the kind of like heavier the checkpoints. So it means kind of like with a new backend for ST, the state can be disaggregated and be stored like in object storage. And it's actually kind of like you pay some latency, but at the same time, for a lot of workloads, you actually don't need that real time, but mostly you care about some balance, some kind of like, I want to understand the trade-off and choose what actually makes sense for me. Because for some workloads, yeah, I kind of like, okay, let it go to object storage.
If you use Flink 2, would you still need to use Fluss?
No, you don't need to use Fluss. Fluss is kind of like a specific, like an extension, and actually kind of like when the guys that invented Fluss, they wanted to kind of like, okay, what problems does Flink have? Okay, they collaborated heavily with Flink team, and they know that new Flink 2 would have a new async execution model, and they proposed this DeltaJoin. And this DeltaJoin was kind of like implemented specifically by the ideas of Fluss, but it's a generic tool. So eventually, if you have a changelog and you can expose some index state, then you can use it. So for example, you can use Pymon as well. But it's just a problem that Pymon actually doesn't support like proper prefix lookups. So it means that you need to do additional aggregations, and that's how you can use Pymon if you wish, as well as Fluss. Yep.
What approach would you suggest, like to join, let's say, multiple Kafka streams, and then later create like an aggregated view, and then push this to like Elasticsearch or some other tool? Like, what approach would you suggest in this kind of use case?
Okay, that's actually kind of like a complicated question because it depends by use case. But basically, I would suggest first to basically collect the trade-offs that you can afford for these separate tables. Because if you have like a 15 joins table, then it's a problem because you need to accumulate a lot of state. But if you need to accumulate this a lot of state for some limited time, for example, let's say for 1 month, then it means 1 month state, it's kind of like nothing. You don't need to use any optimizations, then you just do it. Then there can be a different line of trade-off. Let's suppose that mostly you have the data that is changed during 1 month. And then sometimes, like once in a while, you have a single record that actually kind of like changes the record 10 years ago. Do you need to support like 10 years ago state for this? No, you don't want. So Flink actually provides the tools to do it. So because you can actually kind of like have a side output with this kind of like record that is not matching and treat it as like some kind of a deal queue. So you just accumulate records there, and then you can asynchronously execute some kind of like an additional pipeline. And this pipeline can be as simplistic as go and query your Postgres database. I mean, like in this case, it's acceptable because it's just a single record. And if you can guarantee this kind of like pattern of behavior, then it's totally sensible. If it's not, you can actually batch a lot. So let's suppose that you kind of like once in a while during some corrections of financial data, you receive like thousands of corrections to some 10 years ago data. It's a problem because if you try to query all of these records to your Postgres database, then you can have a performance problems. What can you do? You can accumulate these batches and then send the whole batch to your Postgres database, and it would work. Or you can actually kind of like execute and query this data from Iceberg table, not touching any Postgres. Or you can go to Elasticsearch or other kind of like stuff, or you can actually send to some REST route and do some sensible processing or kind of like bookkeeping. You can actually say like, okay, I know that these records are actually needs to be processed, but I don't care when they need to be processed. So I just save them inside output table, and then I have a Spark job running and kind of like correcting this stuff in my kind of like analytical database. Yep.
Question: do you use Kafka streams at all?
No, we don't use Kafka streams. We've chosen Flink.
Fair enough.
Because yeah, there is also kind of like some kind of limitation because Kafka streams, they tend to generate a lot of intermediary topics, and right now we are actually kind of like running on AWS MSK, and they have a limitation around partitions, so that's why we kind of like tend to use Flink more. That's another reason why we've chosen Flink as our streaming layer.
Thanks, Anton.